What did we study in the previous lab? So we had looked into ALU. Yes, using opcode, isn't it?
Yes, sir.
Yeah, good. So today, we'll be continuing our discussions with the other programs. So we'll be looking into experiment number 4, where we discuss about decoder, encoder. Now again, encoder has two types, the normal encoder and priority encoder. Can you all recall that you had studied these concepts in your previous semester? Decoder, encoder, multiplexer, and demultiplexer.
Yes.
Yeah. Okay. So we'll be, looking into those concepts today, and I think probably we'll be doing decoder, encoder today, and maybe mux and demux we'll be looking into in the next lab. So can someone tell me what is a decoder, if you can remember offhand? Where do we use decoder, and what is a decoder? Okay, so before we look into this, I will just share you are you all able to see this?
Yes, sir.
Yes. So what circuit is this? What representation is this?
3:8 decoder.
Correct. So what do we understand by this 3:8 decoder?
3 inputs, 8 output decoder.
Very good. So which means we are going to have 3 inputs, and we are going to use an enable, and we are going to have 8 outputs. Now, where do we use this? For example, if I have my inputs as a combination that is 2^3. Okay, so 2 raised to 3 is going to give me 2 into 2 into 2. So 2 into 2 is 4, 4 into 2 is 8. So which means I'm going to have 8 combination of outputs from D0 to D7. Now enable is used if and only if if I want to enable the circuit, then only I'm going to use it, right? If not, then I can disable it with the help of whatever value that I'm going to give here. Okay, so now that you have this in your mind, okay, decoder, we will get back to our program, and we will see as to how this is done. Okay, fine. So our aim is to write an HDL program in behavioral model for 8:3 decoder, 3:8 8:3 encoder, 3:8 decoder. Okay, and see, always remember, decoder will have less inputs, more outputs. Encoder will be the reverse of it. Okay, so encoder will have more inputs and less output. So it's the reverse of whatever information that you are decoding, right? Okay, so we'll be using Xilinx ISC. Fine. So an encoder is a combinational circuit. What's a combinational circuit? And what's a sequential circuit? We have seen this, right? Exclusively in digital electronics. Yes, what's a combinational circuit and what's a sequential circuit?
The combination requires clock, sir.
And then what's
Sequential doesn't require.
the main differentiating factor, Tarun? Don't you think it's with respect to memory?
Yes, sir.
Correct. So all of you can recall memory circuits involving memory will be into sequential, and here we say combination where there's no any kind of memory involved, but the output is dependent on whatever kind of combinational input that you are going to give. Okay, fine, good. So an encoder is a combinational circuit that converts binary information in the form of 2 raised to n in the form of 2 raised to n input lines into n output lines, where n represents the code for, or it can be the power of 2. Okay, for simple encoders, it is assumed that only one input line is active at a time. So we cannot have multiple lines active at the same time, right? So that's the basic concept that we have with respect to encoders. So there is another kind of encoder which is called priority encoder. Okay, so this encoder circuit in which the inputs are given priorities. So based on wherever is the priority, that is picked up, and accordingly it is executed, and it appears at the output side, right? So I will show you. Okay, I will show you a few examples as to how this encoder is done before we get into the program, right? So the input with higher priority takes precedence, and the output corresponding to that is generated, right? Okay. A decoder does the opposite job of an encoder. It's a combination circuit that converts n lines of input into 2 raised to n lines of output. So as I showed you the block diagram, right, where you had 3 inputs, enable, and 8 outputs. So your encoder is going to be the reverse of it. Okay, so 8 lines are going to be at the input side and 3 lines are going to be at the output side, right? And as we all know about mux, of course, we'll be dealing with this in our next lab, where a particular input can be selected and it can be given to an output. So demux will be the reverse of it, right? So mux is a combination circuit which have many data inputs and single output, right? So multiple input lines and a single output line. For n input lines, okay, log n to the base 2 selection lines we're going to use, right? So based on how many ever inputs we have, okay, so ultimately that should be covering the select line. So if I have say 4 inputs, okay, then how many select lines do I need?
3.
3. Do we really need 3, or can I work it out with 2? Because I need 0, 0, 0, 1, 1, 0, and 1, 1, right? So all the 4 combinations are covered here with the help of 2 select lines, isn't it? Yes, is it clear? Is it clear?
Yes, sir.
Yeah, fine. So having the select lines, then we can actually check out as to how much of inputs are there, and accordingly we can have the number of select lines, and outputs can be accordingly selected, right? So demux is a device that takes a single input line and routes it to one of the several digital output lines. So here, just like your encoder, it will have more, it will have, it's the reverse of your multiplexer, where a single input and multiple outputs, right? So which is used to select which output line to send to the input. So demultiplexer is also called data distributor. So we will see that, right? Okay, so first let us look into decoder. Yeah, so we will be giving the initialization, right? Library IEEE use IEEE dot standard logic 1164.all, and from here is where we are going to start entity decoder. Okay, 3:8 decoder is port. I'm going to use A for input, and those inputs are going to be 2 down to 0, which means I'm going to have 0, 1, 2, right? So 3 input lines, because this is a 3:8 decoder. Then enable is also going to be a form of input. Then I'm going to use output, which is 7 down to 0. So that is going to give me how many lines? It's going to give me
8 lines.
So here the entity declaration can be entered. So as I was mentioning in our previous lab, you can either write end decoder 3_8 or end entity itself. Okay, just write end entity, because this is where your entity has started, right? So next is our architecture. Okay, architecture name of entity name is begin. So we are going to use process and case statements. In a previous example also, ALU, we have seen process and case statements. So when I use a comma enable, so these two becomes sensitivity list. As soon as there is any change in A, or if there is any change in enable, then immediately that will be sensed, and it will be the output will change according to the changes done in the input side. Okay, now here enable and A, are these inputs or outputs? What is it that we have declared it as?
Inputs.
Inputs, very good. So A, you can see here A in, enable in standard logic. And then we begin, and if enable is equal to 1, then we have one case. So we have case A is, if enable is 1, then case A is when 0, then Y should be giving me this output. Okay, so ultimately, you should understand that, this is referring to the 0th bit, okay, the first bit, second, okay, third, fourth, fifth, sixth, seventh, right? So this is how it works. Let me just share you another document where you'll be able to understand this in a much better way. So I hope you're able to see the screen, right?
Yes, sir.
Yeah. So here, we are looking at different combinations of decoders, right? So anyway, now that we have seen it, it's fine. Let's say, for example, if you have to use a 2:4 decoder, okay, then you can use A0 A1. Okay, so this is A0 and this is A1, and then you connect both of them here, and you'll have one common line, and the inverter will be connected there. So which means either the lower decoder will be enabled or the higher decoder will be enabled. So you have 0 to Y7, so which means 8 combinations of outputs, right? Because we have 3 inputs here, right? And this A2 is going to be our MSB, so which means A0 is going to be the LSB. So it's going to be A2, A1, A0, right? Okay, so now moving on to the next just a complicated type of decoder, right, where I'm going to use a 3:8 2 3:8 decoders, right? So which means going to use from A0, A1, A2, A3. Okay, the same concept here, 3 input lines taken in common, and the enable is also taken in common, so that the lower half, the lower decoder or the upper decoder gets utilized. Now when I use this lower decoder, which means I'm using the lower section of my outputs. Okay, so which means it's going to be Y0 to Y7, or it's going to be, if I'm using the upper decoder, so I'm going to use the upper higher bits, okay, which is Y8 to Y15. So I just wanted to give you a brief idea, about this decoder, right? So yeah, so this is what I wanted you to concentrate on, 3:8 decoder. So when I say 0 here, okay, D0 gets high. Then when I say 1, D1 gets high. So if you can just see the pattern, okay, so if you can just see the pattern, you can see that all these are going high. Yes or no? Yes.
Yes, sir.
Okay, so you can see that it's actually going in this fashion. Okay, fine, as your inputs keeps on increasing. So when I say increasing from 000 to 111, so which means here a D0 will be high, and then D1, and then D2. Okay, D3 is going to be high, then D4, 5, okay, 6, then finally 7. So this is how your tabulation should be. Please make note of this so that you can put it in your observation notebooks. Okay, can I proceed?
Yes, sir.
So in your observation notebook, make sure that you have this tabulation. It's going to help you in easily understanding it. Okay. Are you all able to see the program? Able to see the program?
Yes, sir.
Okay, fine. Thank you. So, so this is how you're giving 0, and this is actually referring to the D0 bit. Okay, so you can rearrange your truth table. Okay, D0 I had written in the left hand side. Okay, so you can put it towards the right hand side and make it an LSB. Okay, so D0, D1, okay, D2, D3, so like that. So as it becomes 111, then the most significant bit goes high. Okay, so this is for these cases. And if we have to consider when others, then give me an XXX, so which means it's just nothing else. If Y is XXX, then we end the if loop. Now remember, we had actually opened an if loop here. So if, and then enable is 1, and so so we were looking into these inputs here, and the two important things that we are going to see here is case and if enable. So that's why whenever there is a change in these two, that's put up in the process, so that becomes our sensitivity list. Okay, now I have opened an if loop here. Okay, so which means I need to end if. Okay, and then before this process was there, so I need to end process architecture, so I have to end architecture. Now what is this else referring to? Okay, so this else is referring to if enable is equal to 0. Okay, so this case, this case A that you are seeing is only applicable if enable is equal to 1. So all this is for enable is equal to 1. So when it says else, it means it is if 1, else, okay, this is also going to give me XX. So which means we have looked at enable is equal to 1, and at this point, okay, and at this point we are looking at the other condition of enable. So here we are going to see for enable is equal to 1, okay, from here to here is for enable is equal to 1, okay. In fact, you know, from here to here, yeah, from here to here we're going to look at enable is equal to 1, and this is taken, okay, others is taken for the combination of 000 to 111. So apart from 000 to 111, say for example, if I give 1000, then what is my output going to be? If I'm going to give 1000, okay. So I've given here inputs from 000 to 111. The next input, if I give 1000, then what is going to happen?
Don't get terms.
Yes, so I am going to get this case here. Okay, so which means it is telling you do not worry, you take only for values, you know, coming up between 000 and 111. Okay, the other values you just leave it, you don't worry about it, right? Okay, so this else y, okay, is actually referring to if enable is 1 and then if enable is equal to 0. So you can end the process and end behavioral, right? End behavioral, or you can end architecture, as I've told you previously. Any doubts here, students, with the VHDL code? Is it fine? Can I proceed?
Yes, sir.
Okay. Now let us see the test bench, right? So we are going to give for enable is equal to 1. Okay, we're going to give all the values, and we're going to say wait for 100 nanoseconds, right? So that's how your test bench is given. Okay, fine. Now let us look into the Verilog code module, decoder 3 to 8, enable A, Y. So enable and A and Y, all three are given in the same, because this is Verilog type. In VHDL, you're not doing that. You're specifically saying what all are your inputs. A is your input, enable is your input, and Y is your output. But here you're not going to do that, you know, with Verilog. You're going to just put them all together in the same bracket, and then you specify them. Input is enable, then I'm going to have A also as input, but it is just like how you use, you know, 2 down to 0. I think this should be 2 down to 0. Okay, so then output is 7 down to 0, right? Then I'm going to use a register, because there's an output here, Y. Now we are going to use an always condition here. Okay, always. So this represents my sensitivity, always at. Okay, so A enable is already there. Then begin if enable. So if I just put if enable, it means it is referring to when enable is high. Okay, you don't have to put if enable is equal to 1, unlike VHDL. See, VHDL, as I told you previously, it was developed by, you know, the Department of Defense and with the army, and they had made it very specific, very strict, and you just cannot deviate from the rules. And hence you can see that, you know, your VHDL had many rules. So the company people, you know, they just wanted to have a lighter part of programming, and it was Verilog came into existence, where this became more flexible, right? Wherein you don't have to mention if en is equal to 1. If you just write if enable, enough. Okay, it is understood. So if enable, then case A. So similarly here we're going to use 3 tick B, which means it's going to be 3 bits, and it's the format is going to be binary 000, and yeah, so this is how we're going to get, and this is going to be 8-bit in binary format. Similarly for 000 till 111, you write the same thing and get the outputs. So by default, okay, this is as good as else. Okay, else you're going to get all unwanted values, which is don't care terms. Then you've started the case here, so end the case else. Okay, so else is referring to if enable is not high, else I'm going to get this. See, the thing that you have to understand here is the programming style. Concept will be the same. Either you're writing in HDL or you're writing in Verilog, concept is going to be the same. The only thing that you have to know is the programming style, the rules. When you're going to use process, how is process mentioned? Am I going to use at in VHDL, or is it used in Verilog? Okay, so when I say process, do I use a parenthesis? Okay, where do I use semicolon? And how do I declare inputs in Verilog? How do I declare inputs in VHDL? Should I use this 3 tick B in VHDL, or should it be used in Verilog? So if you can answer these questions for yourself, then you'll be able to introspect and get to know as to how to write code for Verilog and how to write code for VHDL, right? So here also we are going to have enable, and then you're going to start with 000, okay, to 111, and then yeah, fine, 111, and then hash 100 is nothing but wait for. So you can see your simulation output here. Okay, so when you're having 0, 000, I hope it's visible. Is it visible, students? Comfortable to view? Okay, so you have 000 here, so your D0 is getting enabled, right? So whatever is your values given here, so accordingly you're going to get the outputs in the waveform. Right, then you can click on this view RTL schematic, view technology schematic. So these windows, have you all tried getting these RTL and text schematics? All of you have tried in your previous labs? I think by now all of you know the procedure, isn't it? How to execute the program.
Yes.
Yeah, good. So given your program, check for syntax, and then you can go into simulation mode. Okay, not implementation, simulation mode. And then again you can check for syntax there, and you can simulate it. So once you get the outputs, okay, you can verify it. It's just like how I've shown you here in the waveform window, right? So once this is done, then you can also get your RTL schematic and text schematic or technology schematic. So any doubts here, students, with respect to decoder? Is it all fine with decoder? Okay, so now we'll move on to encoder, right? So which means we're going to do a reverse of it. So port, we are going to have A, okay, and that's going to be input. As I told you, it's going to be 7 down to 0, just the reverse of decoder, right? Enable is used, output. So here output is going to be 2 down to 0. Okay, fine. So this bracket is extra. You don't have to put this bracket, right? Just a single bracket should do. no, it is needed because we are using port here, right? Yeah, it is needed. So the bracket starts from here. Yeah, the opening bracket, and enable Y. Yeah, so it is needed. And then you end your entity, architecture, begin, process, the same way, right? If enable is equal to 1, so the reverse, these all used to be on your right hand side, now it is going to be on your left hand side. Okay, so this is all when A is equal to this value, when A is equal to this value, when A is equal to this value, then Y should give me this. Okay, so yeah, so apart from these combinations, okay, from 000 to 111, apart from these combinations, if I get anything else, or if I have anything else apart from this, okay, now we are not looking at 000 to 111 because these are our outputs, right? So we are going to see only these values here: D0, D1, D2, 3, 4, 5, 6, 7. So apart from these input values, okay, if I'm having anything else, then it should be a neglected value. So here I'm going to end the case for A, okay, here, and else I'm using if enable is equal to 0, then also my output is going to be XXX. Going to end if loop, end process, end architecture. Okay. So just the code remains the same, okay, only the declaration part, inputs and outputs, you'll have to reverse them. Whatever you had declared to output, okay, is going to be to the input side, and whatever you had declared for the input, it's going to be in the output side when you compare both encoder and decoder. And here, you saw that it was towards Y, and now it is towards A, the input side. So you give all these combinations here, okay, when A is equal to all these values, and you wait for 100 nanoseconds between each instruction. Okay, so we take the Verilog code now, and we use module 8:3 and enable. Now let me also show you, how this is. Let me show you the diagram of encoder so that you'll be able to analyze it. Okay, so what is an encoder and priority encoder? An encoder is a digital function that produces a reverse operation from that of a decoder. Yes or no? Do you all agree with this? Is it a reverse operation of decoder?
Yes, sir.
Yeah. And then an encoder has 2 raised to n or less input lines and n output lines. So basically whatever is to the power of 2, okay, that becomes your input. The output lines generate to the binary code for the 2 raised to n input variables. Okay, so let us see one example here that I have written. So D0, D1, D2, D3, 4, 5, 6, 7. Right, so these are going to be your inputs, and your outputs are going to be in this fashion, right? So you can just check. Okay, I have combined 2 truth tables here. Okay, so the number 1 says with zeros in inputs and no valid column. Okay, so if you have to just refer to encoders, okay, if you have to just refer to encoders, then it's going to be the one with zeros, not with don't cares, and no valid column. So which means, let me make it more simple for you. And yeah, so we are not going to have this column, right? And this don't cares will not be taken, right? Only zeros will be taken. Is that clear, students? Yes, you're able to understand now what I'm trying to say?
Yes, sir.
Yeah, so I have combined 2 truth tables here for encoder and for priority encoder. So now let us see only for encoder. Okay, so just concentrate on the zeros here, and of course we are not going to use this valid column as of now. Okay, so your concentration should be only on the inputs and on the outputs. That's it, and on the zeros. Okay, so as usual, I'm going to give 1 and then all zeros, so which means D naught is enabled. Okay, D naught means D0. Okay, so all are 0. Then I give D1. Okay, so here it's going to be a binary 1, right? So accordingly, when D7, if D7 is there, then rest all will be 0, right? 0 0 0 0 0 0 0 1. Of course you can reverse it. Okay, as I told you, you can bring D0 this side and D7 this side, so that you can have D0 D1 D2 D3 4 5 6 7 D7. So you can have it in that fashion. That will look still conventional type. Okay, what I've written here is a non-conventional type, a different way of representing the truth table. So so this becomes your encoder, right? Now let us talk about the priority encoder. So for priority encoder, what are we doing? We are looking at inputs, we're looking at outputs, and we are looking at valid column. Okay, and here we are not looking at zeros, but then we are only concentrating on what? We are concentrating on what? Zeros, or don't care for priority encoder? Don't care. Okay, we are only concentrating on don't care, and zeros we are not taking. Okay, now let us take for example, yeah, so let me take D2 for example. Yeah, this case will take D3. So now here, since D3 is enabled, okay, D3 is made high. So if I'm going to use encoder, D2 will be 0, D1 and D0 will be 0. But if I'm using a priority encoder, everything is going to be don't care, no matter even if the value is 1 here. Okay, let's say that I put let's say I have a value 1 here. Okay, now we are concentrating on this column, on this row. Okay, so just look at it. Okay, so just concentrate on this row which I have highlighted. So here, if D3 is made high, then even though if my D2 is there, okay, then it is not considered. So it is a don't care. So in priority encoder, the priority is given to D3. But in if you take the normal encoder, then suppose a 1 is here, okay, it could be considered. But here it's going to be a don't care. So you should think that in an encoder, it's going to be a 0, and in a priority encoder, the rest of the bits are going to be don't care. Is that clear, students? Don't care is referred to, when is it referred? In encoder with priority or without priority?
Priority.
Yes. So when you're considering priority, take don't care. When there is no priority, that is without priority, then encoder, whichever value is high, okay, the rest of the bits will be 0. Okay, so this is how you should understand your encoder with priority and without priority. Make sure that you even take note of this. I want this also to be in your observation notebooks. Fine. Can we move on to the program?
Yes, sir.
Yeah. Okay. I hope this concept is clear, right? Okay. So you have 8:3, right? Yeah. So 8 bits, and this is going to be your A. Okay. Your output is going to be 3 bits, and in binary format, and 000 till 111. Rest of them you're going to take it as X, and case else, that is if enable is equal to 0. Okay, you take for that also as X. So note here, input you're taking 7 down to 0. Okay, 7 is to 0 in square brackets, just like vector, input vector. So here, instead of using a vector, you're using a square bracket, and 2 is to 0. Right, so end and end module. Fine. So with the test bench, you're going to give all the combinations, and you're going to tell for each statement, wait for 100 nanoseconds hash. So hash is representing the same. So here also the same kind of outputs you're going to see when it is 0. Okay, when it is 1. Okay, so whichever bit is enabled, correspondingly you can look into it. So this is your text schematic and RTL. So in your left hand side, you have both tech and RTL. So when you click on them, consequently, when you again double click on this, you'll be able to see various information, the gates and all those things. Now let us shift our focus to priority encoder, right? So in priority encoder, everything is going to be the same. Just we have to add a few information. Let us look into that. Library, use, entity, okay, port, input 7 down to 0, enable, then Y is going to be your output, standard logic vector 2 down to 0, and entity, architecture, okay, process, A, and enable. So both are active. Begin. If, okay, now here starts the loop. If A7 is equal to 1, okay, then I'm going to have output as 111. So after if, I'm going to use else if, not ELSE, but just ELS. Take note, it's only ELS, ELSIF. Else if A6 is equal to 1, then Y is going to give me this. Similarly for 5, 4, 3, 2, 1, 0. So for 0, I'm going to get my output as 000. Now else, okay, else, which means I'm looking at the other case, okay, else Y is equal to 0. Now this is looking for the enable case, right? Yeah, so it's going to give me a don't care. So end if is here, end process, because we have started the process, and then end architecture, right? So the only thing that we are doing here is we are kind of giving it as a if else statement. If this is there, then this should be my output. If A4 is 1, okay, then my output is going to be 100. Any doubts here, students?
No, sir.
Yeah. So similarly, you can give the same thing here. Okay, you don't even have to change your test bench. You can give the same thing here, just you had used for a normal encoder. Okay, and you can tell them to wait for 100 nanoseconds between each instruction. So similarly, how do we represent it in Verilog? Module, priority encoder, put in all inputs and outputs, then separately declare each input, output. Then here, instead of process, we are going to use always process, case, all this is used in VHDL. It's not used in Verilog. So always begin, just like how you have process, case, here always begin. And these symbols you're not going to use there. Okay. So begin if enable 1. Okay. Then if A7 is 1, okay, that's the 7th bit. Okay, if the 7th bit of A is 1, that's what it is trying to say. Okay, so which means if the highest, the MSB, most significant bit is 1, then output is going to be 111. Similarly, you write it till 0. If A is equal to 0, the 0th bit, okay, which means the least significant bit. If least significant bit is 0, okay, A0 is 1, okay, if that is enabled, then I should be getting 000. So else I'm going to get a don't care, and else if enable is not high, then I'm going to get XXX. Then it's going to be end, okay, and end module. Test bench also remains the same. Okay, you can give in all the cases, D0, D1, D2, right, all those cases, and tell them to wait for hash 100 nanoseconds. Outputs you are going to see in the form of, you know, the same thing that you had seen previously. Okay, you can just try and play around with different things. Instead of you know, you can probably give 2 inputs, or probably, you know, you can just play around with the code, right? And once you're done with the execution, once you've noted down the taken the screenshot of your outputs, okay, you can just change the code and see, you know, what is going to happen if you give this 0. Okay, then what is going to happen? So you can just, you know, tweak your programs and check how your outputs are going to correspondingly appear. So this is going to be your you know, text schematic, the RTL schematic. You can even generate your technology schematic. Fine, students, is it okay for today? Yeah, we have 3 programs.
Test bench, we can take anything of the inputs, no sir, but it's depend on the bit.
All the cases you have to give, that's it. Yeah.
No, like the particular bit will give 1, sir, and the rest all we can give R1, no sir.
You can do that. I suggest whatever you have taken as your input, the same thing you put it in your test bench, because test bench should have all the combinations, right?
Yes, sir.
Yeah. So first you can try it in this fashion, and then you can use your method. That's also fine. No problem. Okay.
Yes, sir. Okay.
Yeah. So I think we'll end this session, students.
Yes, sir.